Good morning, everyone. We are going to discuss a new section today, and this is structural analysis of statically indeterminate structures using approximate analysis. So, this is a method that we can use to analyze particularly portal frames using an approximate method. So there are two methods for trusses. If the diagonals are intentionally designed to be long and slender, it is reasonable to assume that they cannot support compressive forces. So if a diagonal member is long and slender, we can assume it will not support compressive forces. So we can continue assuming that it will only carry tensile forces. Hence the panel shear is resisted entirely by the tension diagonal, whereas compressive diagonal is assumed to be a zero force member. So if you look at, let me see, say here, if you look at this one, how many members are here? So 1, 2, 3, 4, 5, 6, and 2 inside and 2 inside. So 6 plus 4, 10. And the reaction is 2 here, 1 here, 3. Joints is R equal to 3 and 3, 6. So M plus R greater than 2J. So this truss is a statically indeterminate truss. So now what we can do is we can use one of these method. Okay, the method one is, if the diagonal member is long and slender, we can assume it carries only tensile forces. If the diagonal member are intended to be constructed from the large roll section, such as angles or channels, they may be equally capable of supporting a tensile and compressive force. Hence, here we will assume that the tension and compression diagonals each carry half the panel shear force. Okay, so tension and compression carries half the panel shear force. Now if you look at this truss, these members do not look like long and slender. So instead of method 1, we can use method 2. That is, these diagonal members carry, we will assume that the tension and compression diagonals each carry half the panel shear. Now if we look at these two diagonals, one diagonal will carry tension and one will carry compression. So if you apply a lateral force, this will be under tension, this element will be under tension, and this element will be under compression. Okay, so again this will be under tension, compression, this will be under tension. So it should be the other way. So this one will be under compression, this one will be under tension. So similarly, this one will be under compression, this will be under tension. Okay, so now what will happen is what this method 2 says. If I take a section, then I can assume this each members carry half the shear force. So each carry half the panel shear. Now if I look at this element, now if this is the load is not equal, so we had to find the support reaction. Okay, so RA and RC and HA. So so let me see the let me take it to the so approximate analysis. So now here if I mark this one RA and RC and HA, so we balance vertically RA plus RC minus 50, 40 minus 20 is 0. So RA plus RC is 110 kilonewton. If you take moment by A, RC into 6 minus 20 into 6 minus 40 into 3, and 50, due to 50 there won't be any moment because it is acting to the point of rotation, is 0. So 6, 3 and 2, 20. So RC is 20 plus 20, 40 kilonewton, and RA is 70 kilonewton. Now since this is 70, if I cut it like this, then I can take the panel shear. So here what will be happening is, so one will be under, say if I assume this to be under compression and this to be under tension. So let's mark this one F BF, this one F AE, and the reaction is 70 and the force is 50. So if I take equilibrium at this point where I have cut it, then vertically 70 minus 50, then I have this BF acting in this direction, a compression. So if I take a horizontal component and a vertical component will be upward. So that is FB or FBF cos 45 degrees. So this is 3, this is 3, so this one is 45 degrees. So cos 45. Then this component is under tension and it will have a vertical component and a horizontal component, and that vertical component also FAE cos 45 is 0, because it should be in equilibrium. If a structure is in equilibrium, a part of the structure is in equilibrium. Now there are two unknowns, FBF and FAE, but this is the method 2 comes into play, where we assume, if you take a section, we assume the tension and compression diagonals each carry half the panel shear. So each of them carry the half of it. So basically AE, if there is a shear force S, BF is going to carry S by 2 and AE is going to carry S by 2. Both should be equal. So 70 minus 50 S over 2 into, so the shear force is S, and 1 over root 2 minus AE, that is S over 2 into 1 over root 2 is 0. Okay, so now this one, now it's going to get us 70 minus 50 is 20. 20 is equal to 2 times S over 2 root 2. So 2 cancels off and it becomes S over root 2. So S is equal to 20 root 2. So 20 root 2 would be something like 1.414 into 20. So that's going to be the shear force value, and from that we can find if BF as S over 2, so that is 10 root 2, and if AE is equal to another 10 root 2. Okay, so this is a method to solve this problem. Now if you consider the method 1, we assume the one under compression to be zero force member. Then what will happen? Say if I assume one of these to be zero force member, then the entire shear force is going to be carried by a vertical component of this one element. So we will get twice this value as the member force. Okay, so that will happen if you consider one of this as a compression member and a slender. But here it doesn't look like a slender truss because it looks quite compact and both are of the same size. So that's why I assume the second theorem, where you assume that both members carry equal amount of force or half of the shear force that is acting in the panel. The panel you can see. Now once you got these two member forces, you can take another shear force cut here and find these two members using the same method. So then all the diagonals are resolved, then other members can be resolved. So if you take this point, we can find these two members easily. If you know this, we can find this member. So like that we can find other member forces. So by solving one or two member forces, we can bring this truss from a statically indeterminate case to statically determinate case. Now here look at this example. So here the second part, the first method will come into play. Determine, and these forces are approximate, right? The one we find is approximate, not exact, but it's close enough. So here determine approximately the force in each member of the truss. Assume the diagonals can support either a tensile or compressive force. Now if you look at lateral force acting like this, so this will be under compression. So if I assume this member cannot carry compressive forces, I can think of this as a zero force member. So this FEC is 0. So then the entire stability is depending on this member, and this member is going to carry tensile force. Similarly here also there will be compression. So if I consider this this cannot carry compression, so FB is 0. So then FAC is what we need to find. Okay, so now we are going to look at this problem. Okay, so let us take this. I can copy this and Okay, example 2. So since these members are long and it looks slender to me, what I assume, since the diagonal members are long, let me assume they cannot carry compressive forces. Hence, FEC is zero force member and FEB zero force member. So these two members now gone. So if I take the statical determinacy check, members are equal to 1, 2, 3, 4, 5, 6, 6 plus 10. Our reactions are 3 and joints are 6. So M plus R greater than 2J, statically indeterminate. Okay. So now, once we have established this, I can cut a section here. So if I cut a section like that, so I have there's no member here. So FEC zero force member, and I have FEB is there, and then I have the other members having forces. So if I mark this one as compression FEF, if I mark this one as again compression FDC, and this one is compression FED, and there is a horizontal force 8 kilonewton. So if I cut it like this, and if I take equilibrium at this point, which is shear, so 8 is the force acting at point D, and then I had to look at in the cut section what are the exposed member forces. So this is an exposed member force, and this is FEF and DC are exposed member forces, but they are acting perpendicular to this section, so we don't need to consider that. And if EC is a zero force member, so we don't need to consider that. And FEB we need to consider the horizontal component of FEB. So this angle theta, so if I consider tan theta, it is 2 over 1.5, so it is 4 over 3. Okay, 4 over 3. So if I consider that 8 minus FEB cos theta is equal to 0. It has two components, horizontal component and a vertical component, and I will consider only horizontal component. I don't need to consider ED because ED is not exposed. Okay, so I don't need to consider ED. So now FEB cos theta is 1.5 over 5 equal to 8. So that is 0.53 and then 10. So FEB is 80 over 3. So that is kilonewton. Okay. So FEB is found, and FEC is also assumed to be zero force members. So now what we can do, I can take equilibrium at this point and find the member forces. Now here I can find equilibrium at the point D and find FED and FDC because FED is equal to FEB cos theta and FDC is equal to FEB sin theta. So then if I find ED, then I can find the other member forces. So similarly, so now the question is, determine the force in each member of the truss. So I have found FEB, I have found. So equilibrium at point D. So at point D I have a compressive force FED and another compressive force FDC and tensile force FEB. So if I balance horizontally, FED minus FEB cos theta is 0. There's no other external force acting at this point. So FED is FEB is 80 over 3, cos theta is 1.5 over 5. So that is 310. That becomes 8 kilonewton FED. So similarly, if I balance vertically, FDC minus FEB cos theta is 0. So FEB cos theta is 8. So FDC also 8 kilonewton. So now this member I have found to be 26.67. This one is 8. This one is 8 kilonewton. Okay. Now if I come to this point, so here 8 and 8 is balancing here. The vertically this member is a zero force member. So if I take equilibrium at this point, EF becomes a zero force member. Okay, EF is 0, because if I take equilibrium here, I can balance this to 8 kilonewton, and if I balance vertically, I don't have any external force, and FEC is a zero force member, so there's no component balancing, so this is going to be a zero force member. So now this is zero force member, and this is this is 26.67. So I need to find the other 3 member forces. So here I can't find the other 3 member forces, because at one point I can get only 2 member forces. But here also I can assume this to be a zero force member, and this one I can find the value. Okay, for the tension, this one tension I can find the value. So if I consider this one, this is known, this is known, this is unknown, and this is known, this is unknown. Okay, so in this equilibrium there are 2 forces now left, FEA and FFA and FFC. So if I balance horizontally, I can find the value FFC, and if I balance vertically, I can find the value FFA. Okay, I can find FFA. Then at this point, we know this member force, then this is known, this is known, so this is unknown, and this is unknown. So if I cut like this, I can expose and find this member forces. So 8 plus 10, 18 is going to be balanced by a horizontal portion of this, so we can find the FAC as well. Okay, so let us see. So we have found these 88, 26.7.0 and this is 0. So now I need to get a cut and find the other diagonal. So the method I am adopting is the first one, that is diagonal under compression is equal to 0. So I am considering a tensile force diagonal only. So if you apply a lateral force here, this member tend to move towards positive x direction and D will tend to move towards positive x direction. So eventually these members will try to pull it and then they will experience tension. So now if I plot this, okay, if I plot this, then here, then here. So FB and FCA, FB and FCA. FCA is tension, FFB is 0 since it's a long diagonal member. So if I take these forces, external forces, 8 and 10, 8 kilonewton here, 10 kilonewton here. So now 8 and 10 is going to apply a lateral force, and then here this is a zero force member, these two are vertical, only this horizontal component will carry it. So if you balance it, 8 plus 10 minus FCA cos theta. So that is also theta, same as the previous one. Okay, so it's cos theta. So now what we are getting is equal to 0. FCA cos theta is 1.5 over 5, and that is equal to 18. So 3, 10, 6. So FCA is 60 kilonewton. So if I know FCA, now this member is known. Let me highlight this. This is known. 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 Then this is also known, the same one, and here this is known. So the horizontal one is not known, the vertical one is not known. In this point also this is known and this is known, so horizontal one and the vertical one is not known. Okay, so now what we need to do is, if I mark these members, say if I mark this one as compression and if I mark this one as compression, so at this point we take equilibrium C, CD, FE. At C, if you consider equilibrium, horizontally the force FC minus FCA cos theta 0. So FCA cos theta is 18, so FC is 18 kilonewton. Okay, so it is 18 kilonewton. So here it is 18 kilonewton. FCA cos theta is 18 kilonewton. And that is balanced by FCF. Then if you balance vertically at that point, this member is FCB. Okay, so FCB. So vertically FCB, and what are the other forces acting on it? I think I'm making a mistake. No, this is a zero force member, so there is no component, horizontal component. FC, that is this element, minus FCA cos theta, then this has no member forces. So if you balance vertically, FCB minus we have DC as well. So DC also a compression force. So DC is a compression force. FCB upward, FCD downward. Then there's no horizontal component of the zero force member, but there is a horizontal component of FCA. So plus FCA, FCB, so minus FCA into sine theta is 0. So FCB is what we are trying to solve, and minus FCD. CD is 8. Okay, FCD is 8. Okay, FDC or CD is 8. So F8 minus FCA. FCA is 60. Okay, 60, and sine theta is 2/5. So 24. So FCB is 8 plus 24, 32 kilonewton. FCB. Okay. So like that, I can continue to the next point at B and find the member forces. Okay, so that's how we can find the member forces. So in a truss we have two options. Either we choose, the method one is we choose a long and slender member to be a zero force member and do the analysis. Second one option is we can consider, if they are not slender, we can consider if you cut a section considering the two member forces, then if you balance it, you will have these two forces, and in that one will be both will be half of the shear force. So considering that axiom, we can solve many indeterminate truss problems. Then frames. So in the frames, what we do is we use points of inflection as pin joints. Now if you have a frame like that and a load is acting on this frame like that, there will be a point of inflection. So point of inflection is where the points where the moment will be 0. So the point of inflection will be normally in a beam, in a girder, or in a frame. It will be at 0.21 L distance. So if your column is a stiff element, from that column it will be 0.21 L. So at this point we can consider it as a pin and then treat this solution. Okay, so that is the method. So the using point of inflection as pins, if the columns are extremely stiff and no rotation at A and B will occur, then we can consider this option. So 0.21 L will be the point of inflection or the moment 0 points if the columns are extremely stiff. So in reality the columns are not extremely stiff. They provide a little bit of a flexibility. Okay, so in that case we assume that point of inflection to occur at 0.1 L distance from the support. So the beam on the frame is going to be considered as a reality solution. So in that case you can assume this point of inflection or the moment 0 point as 0.1 L. L is the span. So once you have considered it to be a pin joint or the moment 0 point, we can convert that frame into this sort of a situation, this sort of a solution. So there is a 0 moment in the girder at 0.1 L from the support. So it can be treated like this. So you take this simply supported beam out and then solve the analysis. Then you can bring it back and find the reaction as force acting on these little cantilevers and find the moments. Okay. Then here if you look at this, determine the internal moments at joints A and B of the frame. So if you look at this one, this is a little bit of a tricky problem. Okay, tricky problem. So if the column is extremely stiff, we can assume the point of inflection to occur at 0.3 consider 0.21 L, and in practically we can assume this 0.1 L and convert it like this and then solve the problem. So that is how you can approach the frames. Okay, frames. Now determine the internal moment at A caused by vertical axis. So here you can see there are two columns. So what we will do is at 0.1 L we consider moment of inflection, and then we cut that element and treat it like a hanging on a simply supported beam. Calculate or find the member forces and then or reactions, and then you can find the end moment. Okay, so we need to find the internal moment at A. So A is here. So once you know the moments stabilized, we can find the moment at A due to vertical load on the frame. So like this we have to look at few more methods that we can use to analyze frames. So we will need another 2 hours that we missed on yesterday, and I hope that we can find a slot to cover this. Okay, so with this Friday lecture we need another 2 hours to cover the balance, and after that this will be completed. Anyway, this method will not be asked in the mid exam, and generally what we have covered till last week will be covered in the mid exam starting next week. So we can stop here now, and we will continue from here and complete the approximate analysis of frames. So we have few more cases to analyze, and then we have trusses supported by frames, so we need to look at this as well. So we have a little bit of work to be done, so we need about 1.5 hours to complete this. I hope we can find a common time and